Hello, my name is Jeff Messier. I'm a professor of electrical and computer engineering in the Schulich School of Engineering at the University of Calgary. And this is Module 6 in our Circuits 2 lecture series, where I talk about the Laplace transform. Now, what I'm going to do at the start of this module is just to give you hopefully a kind of an intuitive idea of what a transform is and why we use it in electrical engineering. I'm not going to be terribly mathematically rigorous here. It's going to be a little bit of hand waving, but hopefully it will allow you to understand the value of the techniques that we're going to be learning. And you'll certainly see this as the course progresses, because very quickly we're going to make a transition from solving differential equations using integrals, which is what we did in the previous few modules, to solving them using Laplace transforms. And I know personally I use Laplace transforms to solve differential equations a lot more than I use, sort of integrals, like just kind of manually integrating them. And so a big part of electrical engineering is learning different methods for representing signals and systems. And when doing a particular type of analysis, we usually switch to the signal or system representation that makes that analysis easier. And as I said, in particular, the Laplace transform is going to make analyzing differential equations easier. And just kind of as a little bit of a warm up for the concept of transforms, you've already in your first circuits course learned how to represent a sinusoid, for example, in two different ways. So of course we can represent a sinusoid using the sinusoidal equation. So let's say we've got a sinusoid with some amplitude a1 cos omega t plus theta 1. And we would say this is, what we would call a time domain representation. However, it's also possible to represent this sinusoid using a phasor. And maybe we would write it using some sort of bold capital letter X. And the phasor would have a certain magnitude or length that's equal to the amplitude of the sinusoid. And the angle of the phasor corresponds to the phase of the sinusoid. And we would call this the phasor domain. And when you've done AC sort of steady state circuit analysis, and that's something we're going to review a little bit later on in this course, but when you would have done this in your first circuits course, you would have hopefully found that working in the phasor domain to determine the voltages, sinusoidal voltages and currents in a circuit with resistors, inductors, and capacitors is a lot easier when you work with phasors than it is working with the time domain representation of a signal. And so basically what's, we're talking about Laplace transforms, and the question is, what's a transform? It's basically just a mathematical operation that allows us to translate a signal or system from one kind of domain to another kind of domain. Actually, I don't want to define the word transform using the word transform. Let's say it's a mathematical operation that allows us to translate a signal or system from one domain to another. And so the Laplace transform allows us to translate between the time domain representation of a signal or system and representing that signal or system in what we call the S domain. And so when I'm writing a Laplace transform, let's say we've got some signal or just general function of time. And if I take the Laplace transform of that signal, I represent the Laplace transform by this sort of script L and surround what we're transforming with curly brackets. That is going to equal capital F of S. And this represents the signal F in the S domain. So it's a function of S now, and I go from a lowercase f to an uppercase f. And that's just a little bit of notation. If we, transforms can be reversed, or there is an inverse transform. So if we take the inverse transform of f of s, we recover our original time domain signal. And the actual transform operation is an integral. So that looks like, so when we take the Laplace transform of f of t, the actual integral is from 0 to infinity. And we start at 0 because in this class we're going to assume that we're dealing with causal signals. So causal signals exist only for positive values of time. And so we're going to integrate from 0 to infinity our time domain signal with respect to time. So we're integrating with respect to time from time 0 to time infinity. And then we're going to multiply our time domain signal by e to the minus st, where s is this variable s in our Laplace transformed signal. And s is a complex number, and is equal to sigma plus j omega. So sigma is real, and j omega is imaginary. And if during your engineering education, you'll be exposed to a few different transforms. The Fourier transform is another really important one that you'll be seeing. And when you look at the Laplace transform, the Fourier transform, you're going to notice kind of some similarities, right? So what you're going to notice is that when we take the Laplace transform or the Fourier transform or whatever transform of a time domain signal, often we are taking our time domain signal, we're multiplying it by something, and then we're integrating with respect to time. So if we were to just kind of write this down in very rough general terms, we might say that our transform signal is equal to the integral of the time domain signal multiplied by what I'm going to call a transform function, in quotation marks, because that's my term, that's not like an official term. And so we multiply the time domain signal with some kind of transform function, and then we integrate the product of these two things with respect to time. This is what's known as taking the projection of the time domain signal onto the transform function. And just to give us some terms to work with, let's represent the time domain signal as f of t. And let's represent this transform function as z. That's a function of phi, right? So phi is just some variable that we can use to change the characteristics of z. And so getting back to this notion of a projection. So a projection is basically a way to characterize how mathematically similar two functions are, right? So if you multiply f of t by z of phi, and if they're, let's say, quote unquote, similar to each other, then the value of this integral is going to be large, right? So if they're very similar, they tend to overlap, they sort of have the same shape, and when you integrate them, you get something that's fairly large. If f of t and z of phi are not similar at all, if, when one is positive, the other is negative, and so on, if there's not a lot of similarity, then when you multiply the two together, you'll get a product that's sometimes positive, sometimes negative, generally, and then when you do the integral, you get a value that's fairly small, right? So you can think of this integral or this projection as a way of kind of quantifying similarity. Now, we basically choose our transform function to emphasize the properties in f of t that we're most interested in, okay? So for example, let's say we want to determine the frequency content of f of t. We want to know the oscillation frequency of f of t. Let's imagine f of t is a sinusoid. Then we could choose z of phi, or actually, let me write this a little bit differently. We can choose z, rather than being a function of phi, as being a function of the oscillation frequency omega. And we can set this equal to e to the minus j omega, right? Which is just a complex sinusoid, basically. So this is equal to cos omega t minus j sine omega t. Okay? And by selecting this kind of transform function, what we can do is we can take this e to the minus j omega, multiply it by our frequency domain signal, and then we can just sort of sweep the value of omega back and forth. And once we get omega close to or the same as the oscillation frequency of f of t, we're going to get similarity between these two. The product is going to be large, and the integral is going to give us a large value. So we can imagine even a plot where omega is sort of our parameter here, and as we sweep it back and forth, once we hit the oscillation frequency of our time domain signal, omega naught, we get a spike. And if our time domain signal consists of many frequencies or tones, we might get several spikes as we move omega back and forth. So that discussion of z to the omega, that's a little bit of a hand-wavy definition or explanation of the Fourier transform, right? Because the whole purpose of the Fourier transform is to determine the frequency content of a signal. And but I wanted to start there because the Laplace transform is a slightly more complex transform than the Fourier transform, if I can say that. So the Laplace transform uses a transform signal that's also e to the minus something, but s, instead of just being j omega, has a real and imaginary component. So it's actually, we have e to the minus sigma plus j omega, which is equal to e to the minus sigma, e to the minus j omega. So actually, we can think of the Fourier transform in a way as kind of being embedded in the Laplace transform, because we do have this term that allows us to sweep omega back and forth to determine the oscillation frequency of the signal that we're dealing with. However, we also have e to the minus sigma, and this is a real term, right? And so e to the minus anything that's real is just a decaying exponential, right? So this, you can think of this as sort of the oscillating term and this as the decaying term. Because when we work with the Laplace transform, we're interested in determining not just the oscillation frequency of our system, but how quickly that system response grows with time or decays with time. And if that kind of sounds a little bit familiar, it's basically going to allow us to determine the transient response of a system, right? Because the transient response is something that decays gradually as a function of time, leaving just the steady state response. And so you can think of this as helping us to determine the transient component of our response. And you can think of this as helping us to determine the steady state component of the response. So just the plain old Fourier transform is a steady state transform. It doesn't allow for transients at all. The Laplace transform does, basically. And this, again, this is a very imprecise kind of hand-wavy thing. It's not very mathematically rigorous, but it does hopefully give you at least a little bit of intuition. First of all, what a transform is in the first place. It allows us to move from one domain to the other. I haven't yet sort of shown you examples of why it's handy to work in the Laplace transform domain, although we're going to get there right away. And hopefully also I've given you an idea of what this, why transforms are typically sort of integrals of a time domain function multiplied by some sort of other function, and what some of the logic is behind how we select those transform functions. So to get started with actually working with the Laplace transform, what I want to do is start out by taking the Laplace transform of a step function signal. And we've seen the utility of the step function already. We like it because it helps us to model a sudden disturbance to a signal, or a sudden disturbance to a system, or the switching on of a voltage source to a system, or applying a voltage source to a system. And so let's start with that. So we know that the unit step function, u of t, looks like this. At time 0, we have a signal that's 0, and then it jumps up to a value of 1. And what I'm going to do is I'm going to calculate our first Laplace transform using the actual integral equation. As we're going to see, we don't often do this, or we don't always do this. We don't always have to perform the integral. Later on, we're going to start to use tables where the Laplace transforms for certain important functions that we work with all the time have already been calculated, and then we just kind of manipulate the transforms in those tables. But to get started, we'll start out with the integral. So I want to take the Laplace transform of the unit step function, so that's how I would write it. And the Laplace transform is equal to the integral from 0 to infinity of our step function, e to the minus st. Oh, sorry. Up here I forgot the t as well. Please add that in. So I integrate from 0 to infinity, u of t e to the minus st, integrate with respect to time. So of course, at 0, that's when the unit step function jumps up to 1. So this is the same thing as just integrating from 0 to infinity the number 1 times e to the minus st dt. And taking the antiderivative, that's minus 1 over s, e to the minus st from 0 to infinity, which is minus 1 over s, 0 minus 1, which is equal to 1 over s. And so the Laplace transform of the unit step function is just equal to 1 over s. So now, in our earlier modules, we didn't work with just the unit step function. We did two things to it. We scaled it, right? Because we're not always just applying a signal that has a value of 1 volt. We use many different levels, voltage levels. And we don't always throw the switch on our system at time 0. Sometimes we switch the system on a little bit later. And if you remember in our example, we had a signal where at some time t0, it jumped up, and it didn't jump up to 1, it jumped up to some value Vs, where Vs was equal to our voltage source. Right, so this is what we want to do. We want to scale the unit step function, and we also want to be able to delay it. And so what I'd like to examine next is how scaling works when we're dealing with the Laplace transform of a signal, and how time delays work when we're dealing with the Laplace transform of a signal. And in order to understand that, we have to look at something called the properties of the Laplace transform. Okay, so in order to show linearity, what we start out with is taking the Laplace transform of the summation of two time domain functions, f1 and f2, that have each been scaled by a different value. So multiplied by a1 and multiplied by a2. And we want, in order to establish linearity, we want to be able to show that the Laplace transform of this expression is equal to the a1 times the Laplace transform of f1 plus a2 times the Laplace transform of f2. So anyway, we'll get there in a second. Let's just start with this. So we'll take the integral of this expression, a1 f1 of t plus a2 times f2 of t, e to the minus st, integrate with respect to time. Because integration itself is a linear operation, we can divide this into two different integrals. And because a1 and a2 are not a function of time, we can bring those out to the front of the integral. But of course, this integral is just the Laplace transform of f1 of t, and this integral is just the Laplace transform of f2 of t. And so this expression is just equal to a1 times the Laplace transform of f1 plus a2 times the Laplace transform of f2. And so we've established linearity. So if we take the linear combination of f1 and f2 first, and then take the Laplace transform of the result, it's the same thing as taking that exact same linear combination of the Laplace transform of f1 and the Laplace transform of f2. And so if we think back to our step response derivation, we had some input voltage, Vi of t, that was equal to the value of our source voltage multiplied by the unit step function. So if we take the Laplace transform of that, and sometimes I represent the Laplace transform operation as an arrow, and then I'll just put the script L over top of the arrow, then we know from this linearity property that the Laplace transform of our input signal is just equal to this constant Vs multiplied by the Laplace transform of the unit step function which is just equal to Vs over S. So the next thing we'd like to do is take a time shift or delay when we switch on our system by delaying our step function. And in general, we represent a time shift in the Laplace transform as a time domain function f of t shifted by some value a, and a is just the time shift. And then you'll notice we also multiply this function by a shifted version of the step function. And that's just to make sure that our signal is 0 before all the way up to this time shift value, which is something that the Laplace transform kind of needs to happen. So basically we have, let's say we had some signal defined, let's say it's a decaying exponential maybe. This is f of t. Now if we delay this e to the minus, I don't know, let's say 0.5 t. So if we delay this signal, e to the f minus 1, let's say we delay it by 1 second. This then is e to the minus 0.5 t minus 1. And there's nothing really in this function that says it doesn't have a value, or there's nothing in this function that restricts it from having a value really for any value of t, right? But the Laplace transform wants, because we're dealing with causal signals, the Laplace transform wants to be sure that, that the value of this function is 0 for negative time. And if the value of this function is 0 for negative time, when we shift it over, this sort of 0 portion of the signal should shift into positive time. And so what we want is a signal that looks like this. So at time 1, we have our decaying exponential. And then before that, this value is equal to 0, just because it was equal to 0 out here. And the way that we represent that, or the way that we ensure that, is we multiply this by a unit step function that has also been delayed by 1 second. So this is u of t minus 1. And that's just to really rigorously ensure that this signal is 0 for any value before the time shift. And so if we take the Laplace transform of that, because this is 0 all the way up to the time shift value a, we now only have to integrate from a to infinity, f of t minus a e to the minus st dt. So to solve this integral, we do some variable substitution. So let's define the variable x as being equal to t minus a. When we take the derivative of both sides, we get dx, we get dx is equal to dt minus 0, right? Because a is a constant. And we then need to translate our variables of integration. So we know if x is equal to t minus a, t is equal to, obviously, x plus a. And so for our variables of integration, if we're starting our integral at t is equal to a, that means that we start, once we transform over into integrating with respect to x, x is equal to t minus a. So in other words, x is equal to a minus a in this case, or 0. And so the lower bound for our integral is equal to 0. And when t is equal to infinity, x is equal to, again, t minus a, where t is equal to infinity. So it's infinity minus a, or just infinity. And so I'll just put this in a little box. And if we continue our equation up here, that means we integrate from 0 to infinity, f of x, e to the minus st, but t is equal to x plus a. So this is x plus a. dt is equal to dx. So this integral is then equal to 0 to infinity, f of x, e to the minus sx, e to the minus sa dx. This term is not a function of x, which is what we're integrating with respect to now, so we can take it out front. We have e to the minus sa multiplied by the integral from 0 to infinity, f of x, e to the minus sx dx. However, this is just the Laplace transform of f of t, where we've just replaced t with x everywhere. And so what this ends up being is e to the minus sa times the Laplace transform of our function. So this is kind of spread out all over the place, so let me just put this in a little box. The Laplace transform of a shifted version of our time domain signal multiplied by a shifted version of the unit step is equal to just the regular Laplace transform of our unshifted signal multiplied by e to the minus sa, where a is equal to our time shift. And so this is our time shifting property. And so now if we go back to our voltage signal, our input signal, really what we want to do is we want to take the Laplace transform of our source voltage multiplied by a shifted version of the unit step, right? Where we turn our switch on at some time t naught. Now we know from linearity that we can take this Vs and pull it outside the Laplace transform operation. So this is just equal to Vs times the Laplace transform of a shifted version of the unit step function. We know from, so this is from the linearity property. We know from this time shift property that this is equal to Vs e to the minus sa times the Laplace transform of the unshifted version of the unit step function. So this is from our time shift property. And we know the Laplace transform of the unit step function is just equal to 1 over s. And so this is the final answer. This is the Laplace transform of the shifted version of the unit step. scaled up to be equal to our source voltage. So what we're going to do in our next module, we're going to look at how we apply the Laplace transform for the analysis of systems. And we're basically going to take this Laplace transformed voltage signal, this input voltage signal if you like, and we're going to apply it to the same RC circuit that we analyzed a couple of modules ago, but we're going to do it in the Laplace transform domain. And hopefully once that's done, you'll be able to see not only how the Laplace transform is applied to do system analysis, but also hopefully how it makes our lives a lot easier compared to solving the differential equations kind of in a manual way using integrals.